inertia. We already know a little bit about where this is going. Ultimately, the moment of inertia is a measure of the rotational inertia of the object. It's a way of measuring out an object's resistance to changes in motion. If we do the comparison with net force, we know that the way an object behaves is based on its inertia. The way I've been really emphasizing it this year in AP1 is to talk a lot about the effectiveness of a force. And I've tried to bring that into this room a little bit, but I've really been driving it home a lot in AP1 for the qualitative purpose of understanding, what do we mean by effectiveness? And that is simply the effectiveness of your force is played out by how able that force is to change the motion of an object. Now, that all comes down to how much inertia the object has. The same force on different objects will not have the same effect. That's what I mean by the effectiveness of a force. The reason I want to bring this up and the reason why I want to keep driving it home is inertia is a fundamental concept, but it's not one that's easy to really understand. Objects that are moving, I don't have to worry about their inertia. Inertia only comes up if I want to change the object's motion. That's why inertia never even played a role in any of the statics questions. I didn't need to know the object's mass unless it was because gravity was acting on it. When it came to its inertia, it was unnecessary because these objects were static. They weren't changing their motion. Net torque has the same kind of effect as net force in that it's going to cause a change in the object's rotation. It's either going to slow it down when it's already spinning or spin it up when it hasn't started, but it's going to change its rotational speed. It's really all about the concept of change. But this blank here, that's the rotational inertia, what we will call the moment of inertia. Now, the symbol we use there is the capital I. I think you should remember that from last year. But it's important to understand that this is not a vector, the same way that mass isn't a vector. Torque is a vector, acceleration is a vector, so the acceleration has to be in the direction of the net torque, in the same way that net force and acceleration are a vector. But torque is in meter newtons, bless you, and acceleration is in radians per second squared. Now, radians doesn't carry over if there's any other unit there, so the unit of moment of inertia has to produce meters, kilogram meters per second squared, suggesting that all of this has to be the unit for the moment of inertia. So its units will be kilograms meters squared.
What did you say earlier that we'd have to calculate a moment of inertia of 1.3 millimeters?
So what I would like to do, though, is I would like to give you a fundamental understanding of where this I comes from. Meaning, what does it look like? I know you already know from AP1 what it looks like, but since it's likely you might not remember, and because I don't bring up the fundamentals of deriving it, I don't do derivations often, I think that there's good reason to see this. So I want to kind of create a straightforward way of seeing where it comes from. I want you to imagine I have 3 point masses that are kind of connected by a thin, light, massless rod thing. Some way of connecting them together that doesn't contribute to the moment of inertia. And that this can rotate about a pivot point over here. So this whole thing can rotate about this pivot. Now, I'm not suggesting I know what will cause this, but let's say that there is an external net torque on the system that will cause a torque about the entire system in this direction. This is a positive torque since it is out of the page towards you. Now, if this torque acts on the system, this entire system will have an acceleration. Now, this part might not be obvious to you, so let me see if I can't say a few obvious things. First, this mass right here, which we'll call M1. Can you see that at all? Probably not. We'll call it M1, this one M2, and this one M3. These masses are each going to experience accelerations. This mass is going to have the smallest acceleration, A1. And that's because it is the shortest distance away from the pivot point. Its top speed will be slower, so its acceleration will be slower. But at this instant, it has a linear acceleration. That linear acceleration, which would be what we would call the tangential acceleration, I'm going to label A1. In the same way that there is going to be a larger acceleration on mass 2. R for mass 2, I'll just say is R2, but it is the fact that R2 is larger than R1 that A2 will be bigger than A1. Remember, it's going to have a higher top speed because it has to travel in a bigger circle. Stating the obvious then, A3 will be the largest of the accelerations because M3 has the largest velocity once this thing is rotating. And it's located a distance R3 away. Now, the reason I bring all those up is the only way any of those masses actually accelerate is if there is a force acting on them. This force comes from the rod. So each of these experiences a force. This one must experience a force F1. This one must experience a force F2. And this one a force F3. They all must experience forces, or they wouldn't have an acceleration. Now, I hope you guys realize that an instant later, the system begins to rotate, and all these accelerations and forces change direction. But for this moment, this single instant in time, there is 3 forces acting, one on each mass, causing 3 accelerations, one on each mass, and each one is a different radius away from the pivot point. Everything okay so far? Now, it shouldn't take too much for you to understand. Oh, I didn't want to do that, clearly. I want to move all of this up so I have more space to... Oh, I'm just going to do it this way. I'm going to erase all this. And I'm going to work up here for just a minute. I mean, F1 has to equal M1A1. It's the only force acting on mass 1. And F2 has to equal M2A2. And F3 has to equal M3A3. Now, this part might be harder for you to understand, but F1 causes a torque about the pivot point, and the torque about the pivot would be F1 times R1. This has to be the torque acting on mass 1. Mass 1 is experiencing a torque at the same time that it's experiencing this force because it's connected by the rod. In the same way, F2 is experiencing a torque because it is connected by the rod. It's just at a different position on the rod. And of course, F3 is also experiencing a torque because it too is connected by the same rod. So the net torque in the system has got to be the sum of the individual torques. Now, whether I had 1 point mass or 100 point masses, you understand it will be the sum of all of those torques acting on every one of those masses. Are we good so far? Now, just between you and me, this isn't the only thing happening here. Other things are happening at the same time. The moment this begins to move, there is another force on each of these masses towards the center. This is what keeps these masses from sliding outward on this rod. But that force only exists once the system starts moving, because that's the centripetal force. So I'm not talking about that force. I'm just talking about the force that is causing these things to rotate. I'm going to go to another page because I've kind of filled this up. Is that all right? Look, Newton's second law and the definition of torque. The net torque on the system, you guys can't read red, sorry. The net torque on the system is going to be torque 1, which is R1 times F1, plus torque 2, which is R2 times F2, plus torque 3, which is R3 times F3. But we already know that we can write each of those forces as M1A1, all right, in terms of the mass and the acceleration of that mass. Now, this part might be harder for you to understand, but A1 has got to be R1 times alpha. Just like A2 has got to be R2 times alpha. And A3 has to be R3 times alpha. And it's the same alpha for all of them. That's going to be R1 times M1 times R1 alpha, plus R2 times M2 times R2 alpha, plus R3 times M3 times R3 alpha. Now, the only thing that is the same for all of them is alpha. Everything else is dependent on that mass and where it is. So if I collect all the alphas, inside I get M1R1 squared plus M2R2 squared plus M3R3 squared. And that has to equal the net torque. Now, for those of you who don't appreciate or don't see what happened or what I did, I showed that the sum of torques produces the moment of inertia times an acceleration. This is a proof of Newton's second law based on Newton's second law for torque based on Newton's second law for force. It is also a proof that the moment of inertia is equal to the sum of individual masses and their distance away from the axis of rotation squared. This is the point mass definition of moment of inertia, proven to you by looking at point masses. Now, I know this isn't a huge deal, and not a lot for you guys to take in, but the moment of inertia is a measure of the distribution of the mass. And an important complication here is that where that mass is the r squared portion of this. This r represents the perpendicular distance from the mass to the axis of rotation. This is something students will mess up quite a bit, and I want to make sure that we don't. Yes, r represents the perpendicular distance from that point mass to the axis of rotation. I mean, put in your notes as the shortest distance from the mass to the axis of rotation. Consider this example. This is going to be our point mass example. I'm going to go square instead of rectangle, but I'll make a comparison to a rectangle in a minute. I want you to imagine that I have a square that connects 4 point masses, each of mass m. So m, 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 m. We can call this mass 1, mass 2, 3, 4. Okay? There are a number of ways to spin this system, and each way is a different moment of inertia. Now, some of them might end up being the same value, but let's consider 3 possible axes. So can somebody give me a possible axis? Center? So, oops, that's not very center. So maybe like this. That's a good one, sure. So this is axis A. Can somebody give me another possible way of spinning this system? Yes?
Diagonal.
Diagonal. Call this axis B. And let's go with at least one more. Yes, sir?
Could you spin it where it's out of the board?
Sure. So out of the board, where do you want me to have my access point?
Center?
Okay, so here, that means an axis coming out of the board towards us, where it would spin like that. All right, 3 separate axes, A, B, and C. Each axis has its own moment of inertia. So in trying to compute the moment of inertia, we're going to do a summation. Now, I hope you realize that some of these summations are pretty straightforward and are very repetitive. Let's consider the moment of inertia about axis A. Can we agree there's a little bit of symmetry here? So I think we can exploit the symmetry. Let's say, since it's a square, that the length of a side is s. Then the moment of inertia about axis A is going to be 4 times whatever the moment of inertia is for mass 1. Wouldn't you agree? Isn't every mass the same distance away from the axis of rotation? So I could say it's m1 times s over 2 squared and keep adding that together, but m1, m2, m3, and m4 are all the same mass. So, exploiting the symmetry, I'm just going to take this and multiply by 4. From here to here. Is that okay? So, can we all agree then that this is going to be ms squared? It's a moment of inertia about A. You good working that out okay? Is that right? Any problem with that? S squared over 4 times 4. So I can move on. That's example 1. So how about this one? If I look at axis B, and I want to spin this system about axis B, 2 of the masses don't contribute in any meaningful way to the moment of inertia. Mass 2 and mass 4 both lie on the axis of rotation. So they on their own have an R of 0. I don't have to add their contribution to the moment of inertia. It's if their mass doesn't even count. On the other hand, mass 1 and mass 3 do count, but we need the perpendicular distance from the axis to mass 3, or the axis to mass 1. Can you figure that out? I mean, I know I can. So let me say this differently. Please figure that out. This is still S over 2. So this must be S over 2. I think you've done this kind of square work before, but I'll give you guys a minute, and then I'll pick one of you to help me out with what that distance is going to be. Logan, did you get it? What's that? I don't think it's S squared over 2. Sorry, dude. Can somebody help Logan out?
I'll try.
Okay, it's your birthday.
Is it S?
It's not S. Sorry, dude. Sorry? Square root of what?
2s squared over 2.
Close. Yes?
Square root of S squared over 2.
That's true.
That's true.
We're so far.
What he said was, if I interpreted it right, the square root of S squared over 2. Or S over the root of 2. Now, look, I can be disappointed that not everybody could get this, or I could just remind you that it's S squared over 4 plus S squared over 4, take the root. That's the Pythagorean theorem every time I've done it. Yeah, because S over 2 squared is S squared over 4.
Oh, just put this. Oh, okay.
Wow. That was rough. That's much harder than it should have been. But let me be honest, this isn't the hard part, right? You got to do the algebra. You can't script the algebra here. But I'll look to the side on that and assume that I didn't see it. The number of you who couldn't do that. Because that's just going to make this S squared over 2, right? And how many of those will there be? Two of them, because there are two of the masses that are located that far away. So when I put all that together, the moment of inertia around B is the same as the moment of inertia around A. Now, it's coincidence, kinda. Keep going. Now, the moment of inertia around C. Every single one of those masses is going to contribute to this, isn't it? Every single one of them is going to rotate. They're all going around in the circle. What distance away from the axis are they? That's right, S over radical 2. Because we're using the same distance away. It's this blue line, the blue dotted line. So it's still going to be m times S over radical 2 squared. How many of these masses contribute? So, the first takeaway. This one is twice as big as the other two. It is twice as difficult to rotate this system about that axis than it is the other two axes. I'm not sure that's the hardest way to spin it, but of these three axes, it sure is. The fact that the first two are the same, coincidental kind of. Those two masses are just far enough away from the axis of rotation in axis B to increase their moment of inertia as much as the other two masses were before. So clearly, distance away from the axis of rotation is a big deal. Now, there were other axes you guys could have chosen. You just didn't. You could have chosen an axis through, say, those two masses. Would have been another one we could have tried. You should try it. Mostly because it's probably going to be 2ms squared. Now, we've done some practice with point masses. You will have to be proficient with point masses. And if you've come to the conclusion I have, most of these are about figuring out some geometry. Triangles and squares and rectangles and garbage like that. Yeah, I'm expecting that that's not going to be too much trouble. Maybe brush off those cobwebs so you can get S over the square root of 2 without me having to call on 4 people to do so. Fair enough? All right. Let me point out one little thing. What was the mass of this system? 4m is the mass of this system. Did the mass of this system ever show up in any of these? The mass of the system? No. This is important. Most of our moments of inertia will be in terms of the mass of the system, but point masses tend to not be. But don't be complacent. If I say that capital M is the mass of the system, and you're supposed to put your answer in terms of the mass of the system, then this one would have been 1/4 capital M S squared. That's now in terms of the mass of the system. Similarly, 1/2 ms squared. Now these are in terms of the mass of the system. All rigid body moments are in terms of the mass of the system. And it is not out of the question for you to be asked to put these in terms of the mass of the system as well. Especially if the object's moving and rotating at the same time. You'll need the mass of the system. Its momentum, its kinetic energy, it's all based on the mass of the system. All right.